The next key idea that I want to get across is the idea of similar triangles having exactly the same trig ratio. So it's this idea that they're saying here that values of the functions are constant for a given angle measure. They do not depend on the size of the right triangle. I'm going to do this with a couple of right triangles that should be familiar to you, and if they're not, they're going to need to be familiar to you. A 30, 60, 90 right triangle. So I'm going to look at two different ones here. These two are similar triangles by the angle-angle similarity theorem. If two triangles have two angles that are the same, then they must be similar, and that's what we're looking at here. And if they are similar, then the corresponding sides have to be proportional or in the same scale factor, which means if each side has to grow by the same factor, whether it's doubling, tripling, or a half of it, or a third of it, whatever it is, but they're all going to grow at the same amount. So what I aim to do here is show you that it's this 30-degree angle. What we're going to do is we're going to look at this 30-degree angle as our theta. And if theta is 30, does it change if the size of our triangle changes? So the first thing I'm going to do is I'm going to just experiment with the sine of the 30-degree angle of the small triangle. So the sine of 30 in the small triangle is, okay, well in the 30, 60, 90, the sides have ratios of a 1, 2 to square root of 3. That's typically the base triangle that we work with the 30, 60, 90 right triangle, so it's always kind of good to memorize those. You can verify that this is going to work in a right triangle if you use Pythagorean theorem. Times square root of 3 squared. And 4 equals 1 plus 3, so 4 equals 4. So these are typically the three numbers that we have memorized for a 30, 60, 90 right triangle, because they're kind of our base formula idea. So if we do the sine of 30, it is 1 over 2, 1/2. Now I'm going to do it for the larger triangle. So the sine of a 30 for the larger triangle, well, since the triangles are similar, I'm just going to throw in here scale factor, a simple scale factor. I want to make sure our scale factor is a scale factor of 2, which means I want the new size to be twice as large. So if we have a scale factor of 2, then our new length here is 4. Our new length on the corresponding side over here is 2. And our new length on our corresponding side down here is going to be 2 times the square root of 3, twice as big. So we now examine the sine of our 30 of our big triangle. It's going to be 2 over 4, which is equal to 1/2. Now this is going to occur every time you have similar triangles. If their triangles are similar, the sine of the 30-degree angle is going to be identical every time, because when we do this, we take out our scale factor 2 times 1 and 2 times 2. Since our scale factor was 2, we can eliminate those and reduce our fraction. We're going to get the exact same ratio. And that doesn't matter if you explore the same thing with the cosine of a 30. For the small triangle, the cosine of 30 is the adjacent side, which is the square root of 3 over 2. The cosine of a 30 on the bigger triangle is, so adjacent, which is 2 times the square root of 3 over 4, which will reduce down to, again, square root of 3 over 2. And finally, if you explore the tangent of a 30-degree angle of the small triangle is, we need the opposite over hypotenuse, which is 1 over square root of 3. I'm going to leave it that way this time. And the tangent of 30 on the bigger triangle is going to be the opposite, which is 2 all over the adjacent side, which is 2 times square root of 3, which does reduce down to 1 over square root of 3. Again, what I want to be emphasizing here is the fact that it's the angle that determines the size of the ratio back here. If it's 30, it'll always be 1/2. I don't care if it's a larger or smaller version of it, because all we're going to have are similar triangles, and those ratios have to grow by that same scale factor, which will end up reducing by the time we write the ratio. So one of the things I want to point your attention to is a key concept when your textbook, trigonometric values of special angles. There are 3 really special angles that we're always going to be emphasizing: a 30, a 60, and a 45. And the sine of a 30-degree angle is always going to be equivalent to 1/2, which we just saw in our previous example. The cosine of a 30-degree angle will always be the square root of 3 over 2, and that would be true if I were to go back to our previous example. And finally, the tangent of a 30-degree angle will always be the square root of 3 over 3, which If we went back to my previous example, if I would have rationalized this denominator, it would be square root of 3 over 3. So it's the angle that determines the value of the ratio, the trig ratio. It is not the size of the triangles. Triangles can grow and shrink in value. The other one that I want to point out here is the 45, 45, 90. If these two triangles both are right, and there's a 45-degree angle here, then in each corner there has to be a 45, so these two triangles are similar. Now the base triangle we normally memorize for 45, 45, 90 is a 1, 1, square root of 2. Again, we can verify this with Pythagoras. Square root of 2 squared would have to equal the 1 squared plus a 1 squared, which is 2 equals a 2. We're going to be just fine with our Pythagorean theorem. But if we happen to grow this thing, and this time if I want to grow this by any factor that we want, again, the easiest growth factor that I can do with this is 2, even though the picture won't look like it. If I double it, it'll be 2 times the square root of 2. If I double this one, it'll be 2. And if I double this length, it'll be 2. And those two triangles have to be similar because of our angle-angle similarity, so every side gets doubled. So now if we start looking at our sine, cosine, and tangent, the sine of a 45-degree angle is equal to, well, the opposite, which is 1 over the hypotenuse, 1 over square root of 2, which is the square root of 2 over 2 in simplest terms for a 45. Then if I take the sine of the larger triangle, which I used a double the size, so it will be the opposite side, which is 2, over the hypotenuse, which is 2 times the square root of 2, and the square root, or the 2's will cancel, so it's 1 over square root of 2, which will, again, be rationalized square root of 2 over 2. And that will hold true for sine, cosine, and tangent. I want to cut this off now just because I think the point probably has been made that if you have, it's the angle that determines the ratio, it's not the size of the triangle, because they'll all be similar triangles based on the angle-angle similarity theorem. So there are some nice numbers here in the table that we're going to see over and over. We're going to want to know these, and basically we'll have them memorized by the time that we're done for a 30, 60, 90, and a 45, 45, 90 right triangle. So I'm going to conclude that, and then we'll go look at some examples how we're going to apply that information.